Hello and welcome to CS170 Section 1. Just as a disclaimer, this is not going to be a regular thing. We are providing this worksheet walkthrough because we realized that not all sections got through a lot of it, and this is not meant to be a substitute for real section experience. So don't expect to have these videos every week and stop showing up to section. All right, that being said, let's get started with a little bit of a mini lecture. So first of all, let's review what O notation, omega notation, and theta notation means. So when we say that a function is O of something, let's understand this with an example. So let's say O of n. What this means is that the function is upper bounded by n. So for instance, the function 1, or any constant really, 3, n, log n, log n, but not n squared, because n squared is not upper bounded by n. What about omega? Big omega is something that is lower bounded. So for instance, let's say we have omega n squared. What does omega n squared mean? Well, it's lower bounded by n squared. So n squared falls in here, n cubed falls in here, not n, because n is not lower bounded by n squared. What about log n? Well, again, log n is not lower bounded by n squared. So no log n. 2 to the power n falls here because exponentials grow faster than polynomials. And finally, what about theta notation? So for theta notation, let's say theta of n again. Theta means that it's both upper and lower bounded by the same function. So in this case, n would fall here, 3n would fall here, 4n would fall here, n squared would not fall here, log n would not fall here. All right, so now we've established what O, omega, and theta represent. So big O says that this is an upper bound, omega says this is a lower bound, and theta says that this is the tight bound. That being said, let's move on to what Master's theorem is about. And I'm gonna try and help you help you think of a way to remember Master's theorem, and hopefully this will help not needing to write it on your cheat sheet, or it's not just some obscure formula, but let's try to develop some intuition for the master formula. All right, so let me erase all this. Cool, so what is the master formula? Well, master formula applies for recurrence relations of the form T of something equals A T n over B plus n to the power D. Now what's going on here is that, so let's learn how to read this. Let me write T of n. So to read this, this says a problem of size n can be solved by solving A problems each of size n over b, and this is the amount of additional work required. So first I want to give you an example. Let's just think about merge sort. In merge sort, if you have an array of size n, you can solve that problem by solving two smaller merge sorts, each of size n over 2. Now, if we have two halves sorted individually in merge sort, after that we need to take a linear amount of time over the entire array to create our big array, because we need to figure out, where do things fall relative to each other, and that you need 2 pointers, and then you move forward, something like this, and this takes O of n time. So O of n. Actually, it's theta of n, because no matter what, we need to move through the entire array. So we can say theta of n. And then we put our T of n here. So this is how you develop recurrence relations. How many subproblems are you solving? What is the size of each subproblem? And how much work do you do after you have solved the subproblem? So this is the additional work. This is how I like to read it. Now, if you have recurrence relations of this form, the master theorem gives you a nice way to solve these. Let's look at what it is. Okay, so the master theorem is as follows. It says that so what is going on here, like I said, is there's a recursive step, which is this step, and there's an additional work step. So this is the additional work step. Master theorem essentially encapsulates what I like to think of as a tug-of-war. There's some work happening here, and so this might be the dominating factor in our total work done, or there's some work happening in the recursion which might be the dominating factor. So we need to figure out which one it is. So in some sense, we have two candidates. For n to the power d, we have d, and for the recursive level, we have log base b a. So let's think about what a is. A is growth, right? Because we have a subproblems. And b is shrinkage. So in some high-level sense, let's say we have something like log 2. This says that the problem, we solve two subproblems, but each one reduces in size by 2. So really, the ratio, roughly the ratio of growth and shrinkage is about the same. Well, what if we have something that's like this? Now, our growth is bigger than our shrinkage. And this number is actually going to be now bigger than 1. Right? Because we know that log base 2, 4 is 2. So, and log base 2 of 2 is 1. So that means this number is actually bigger than 1. So this says, OK, well, you were growing faster than we are shrinking. So there's some work happening here. And we compare these two functions, well, d and log base b a. And then it turns out that the final runtime is, depending on which of these two is bigger, is n to the power d. If d is greater than log base ba, it is n to the power log base ba. If log base ba is greater than d, if they are equal, then it is n to the power d log n. So this is this level is sort of like the tug-of-war is in perfect balance in some sense. And to see how exactly this derives mathematically, you should follow the proof in the textbook. It's written as well as I can possibly explain it. So if you have questions, post on Piazza. All right, cool. So now that we've established master theorem and we have some sort of sense of how to remember it and apply it without having to refer to a cheat sheet again and again, let's move on and try to solve some of these recurrence relations. And then let's see what happens if we are not able to apply the master theorem. OK, so I'm going to move on to over here, which is I can't write on this. OK, well, 1a. And let's try to figure this one out using the master theorem. All right, so I'm going to erase the stuff at the bottom and keep the thing at the top so we can compare. Let's go. Cool. So taking a look at part A, well, A is 4, B is 2. So we already noticed that it grows more than it shrinks. So this is grows, this is shrinks. And in this case, D is actually just 1. So as you would notice, there's something missing here, which is this O. But here's the thing. This can be O or this can be theta. And depending on whether this extra work is O or theta, the master theorem gives you a bound in O of theta. And why does this make sense? Well, if you say that the upper bound of the work that we do, that the extra work that we do is, like n cubed, that's an upper bound. You could just be doing constant work at some levels. If you say that the theta bound of the work that you do extra at each step is like n cubed, then every step you do n cubed work. And so the master theorem is also going to give you a theta bound. So I hope this makes sense because some students were confused about this. But if not, again, feel free to follow up. OK, so we have A, B, and D. And we ignore the 42 here because that's just a constant factor. And we don't worry about constant factors in asymptotics. Now let's take a look. Well, what is log base BA? It's 2 because it's log base 2, 4, which is 2. And D is 1 versus D equals 1. Which one wins? Well, this one wins. So the answer is n squared. Is it theta n squared or O n squared? So in this case, when we haven't actually written O or theta, this is considered to be like exactly, we do exactly 42n work. And 42n is theta of n. So this is a theta bound, theta of n squared. All right. I'm going to, at this point, encourage you to pause and try to do part B on your own. So I'm going to count to 5, pause. 1, 2, 3, 4, 5. All right. If you work this out, let's figure it out together. If not, that's up to you, but I really think you should pause and try it out. Okay. So we have this time for part B, A is 4, B is 3, and D is 2. Well, let's figure out what log base BA is. So in your exams, you aren't allowed calculators, and you might be like, I don't know how to calculate log base 3 of 4. That's okay. What you do know is that log base 3 of 3 is 1, and log base 3 of 9 is 2. So indeed, log base 3 of 4 is going to be somewhere 1.1 something. Maybe it's 1.2. I don't even know, but it doesn't matter. Because we just need to compare this to 2. 2 is bigger. Great. And again, over here when we say plus n squared, we mean theta n squared. If there's no O bound, it means theta. So in this case, what's going to happen? Well, the answer is going to be theta n squared, because n to the power d in this case. All right. Now, for the next part, we already start to see this is not what the master theorem looks like. In general, when things look like this, we cannot apply master theorem. So let's see what we can do. There are alternate techniques to solving this. And one of the reasons we teach the master theorem in this class is to show you that, it works for certain kinds of recurrences, but it doesn't actually quite work for all of them. So it's not this, it's called the master theorem, but it's not this superstar one solver for any problem ever. So while it's good to know, also know how to do it manually. So let's work it out. Let's see. Okay, now our recurrence looks like Tn is equal to 2t n over 3 plus t n over 3 plus n squared. When you see something like this, or when I see something like this, there are two ways I like to think about it. One is, well, t n over 3 is just a recursive definition because we know what t of something is. So we can apply, for instance, in this case, t of n over 3 can be written as, well, 2t n over 9 plus t n over 9 plus n over 3 squared. This is one possibility, and we can plug this in here, plug this in here, and see how the math works out. That works, but I tend to find that it becomes quite messy, quite fast. So I like to draw the same idea as a tree, and let's see how that works. So we have a problem of size n to start. So let's make a node n. This node does an extra n squared work. Remember that, right? So let's make a note of that. Extra n squared work. Cool. Now this node splits up into 3 different recursive calls. So there's one recursive call of size, my bad, I messed something up. This is supposed to be a 2 here. So just a quick thing, this is supposed to be a 2. So this is going to be of size 2n over 3, 2n over 3, and n over 3. Now, how much work, remember these are 3 separate recursive calls, and they each make further subcalls, but they also do some amount of work. So how much work does this one do? Well, it does, remember, if the input is n, so if the input is n, then you do n squared work. If the input is 2n over 3 now, you do essentially 2n over 3 whole squared amount of work, which is 4n squared over 9. Cool, so this one does 4n squared over 9 work. This one also does 4n squared over 9 work. And this one does n squared over 9 work. What does this sum to? So we usually try to think of trees in levels. And at this level, how much total work is happening? Well, 4n squared plus 4n squared plus n squared, 9n squared over 9, n squared. Aha, so we started off with n squared work. Next level, n squared work. And on this level, we do n squared work. Now, let's split this up one more time and see what happens. So when I split this up into 3, I'm going to get, what am I going to get? So I'm going to get 2n over 3 times 2 over 3, right? Because we split it 2 over 3 times. So this is going to become 4n over 9, 4n over 9, 2n over 9. Similarly here, 4n over 9, 4n over 9, 2n over 9. This one is going to become 2n over 9, 2n over 9, and n over 9. Let's see how much work happens in the total thing, right? So each one just gets whole squared. So first let's just take a look. All the denominators are the same. So the denominator here is going to be 9 squared, 81. And the numerators, we need to sum them up. So 4 squared plus 4 squared plus 2 squared plus 4 squared plus 4 squared plus 2 squared plus 2 squared plus 2 squared plus n squared. You can check this out. This is going to be equal to 81n squared. Nice. So even on this level, we do n squared work. OK. Well, it seems like that at every level we are doing n squared work. Well, the only thing we need to do then is how many levels are there, right? Because if we know that we do n squared work at each level and there are like x levels, then the total work we do in this whole thing is n squared x. So let's try to reason this out. How many levels are there? Well, this one is actually kind of tricky, right? Because while these nodes are splitting, OK, so let's figure this out. These nodes are splitting at a ratio of like 2n over 3, which means n over 3 over 2 or n over 1.5. So essentially, these nodes are becoming 1.5 times smaller each time, whereas this node is becoming 3 times smaller. So there's a disparity, right? This one keeps becoming 3 times smaller. If we started off at 27, this one's going to become 9, then 3, then 1. It just takes 4 steps, or it takes log base 3 of n steps. So again, n over 3 side takes log base 3n steps. The n over 3 node keeps splitting, and it takes log 3n over, well, not steps, but levels, right? So in some sense, this one is going to finish as soon as we have log base 3n levels, which means this one gives us n squared log base 3n as our answer. But what about the other one, you say, right? So let's try to do this trick where if we can lower bound by some function and upper bound by some function, then we actually have a theta bound. So in this case, we can say that this is a lower bound. Why can we say this? Essentially because we know that this one will end, but this one still will keep going. And so this one ends first. So there'll be more work happening, but this is at least the amount of work we need to do. Great. So let's reason this for the other side now. The other side is going to have, similarly, log base 1.5 levels. But this one is going to run out. So the n over 3 is going to just finish, essentially. This one's going to keep going. So what happens is, now you think to yourself, well, if this one runs out and this one keeps going, then we don't actually have n squared work happening at each level. Good. But here's the realization. We have less than n squared happening, right? Let's see if I can erase some stuff and explain this better. But essentially, somewhere down here, we're going to hit a level where this one is done. And so we have just some people left here. Now, the sum here is not going to be n squared. It's going to be less than n squared. Cool. Since they're all going to be less than n squared, let's upper bound it. Let's say, well, it's just n squared. It's n squared. It's n squared. So by doing that, we have n squared log base 1.5n, right? Because we have log base 1.5n levels, and we do n squared work, n squared work, n squared work until some level, and after that, less than n squared, less than n squared, less than n squared. Let's upper bound that. Now we have omega and O. And notice how they differ by a constant factor, because you can change the base of logs by multiplying by a constant factor. So this results in theta n squared log n. Cool. So this one was a lot. Make sure you understand this before moving on to the next one. But at this point, again, I'm going to encourage you to try and do the next one on your own. I'm going to count to 3 this time, and you guys can pause the video. So 1, 2, 3.
In the previous part, we saw how we can use tree diagrams to reason about recurrence relations. Now in part D, we have a recurrence relation T of n equals 3t of n over 4 plus n log n. So the first thing to notice is, again, like the previous part, we can't really use the master theorem in this case. And so we'll try to take a little bit more of a mathematical approach. So let's see if we can solve for the value of t of n over 4. So we can do this just by substituting into our original recurrence relation. And this gives 3t n over 16 plus n over 4 log n over 4. All right. Now let's substitute this formula back into our original recurrence relation. And this gives us that t of n is equal to 3 times t of n over 16 plus n over 4 log n over 4 plus n log n. And expanding this out a bit gives us 9t of n over 16 plus n over 4 log n over 4 plus n log n. All right, so just to see if we can find a general pattern, let's substitute another layer down. So let's solve for t of n over 16, which again is just going to be 3t of n over 64 plus n over 16 log n over 16. And substituting this back into the formula we just got up here, we find another result for t of n, which is going to be 9 times 3 t of n over 64 plus n over 16 log n over 16. Plus n over 4 log n over 4 plus n log n. Okay, and so when we expand that, we get 27t n over 64 plus n over 16 log n over 16 plus n over 4 log n over 4 plus n log n. So essentially what we've shown is t of n can be written in terms of many different subproblems, all of which are powers of 4. It can be written in terms of t of n over 4, t of n over 16, or t of n over 64. And we've shown the relationship for all 3 of these cases. So take a minute to pause the video and go through these steps if you don't understand it yet before we move on. So by what we showed in the previous part, we can notice that we've now come up with 3 equivalent expressions for t of n, one in terms of t of n over 4, one in terms of t of n over 16, and one in terms of t of n over 64. So looking at the general pattern for this, we can see that more generally, t of n is equal to 3 to the k t of n over 4 to the k, plus the sum from I equals 1 to k minus 1 of n over 4 to the I log n over 4 to the I, where k equals the tree depth. Okay, so now that we have this final expression, we're going to make an assumption. We're going to make the assumption that at some point our recursion bottoms out, and let's say that case is when we have t of 1. And for simplicity, let's say that is equal to 1. Essentially, all we're doing here in this assumption is saying at some point the recursion will end and will require just a constant amount of work to do. Okay, so let's see when, at what depth this occurs. To solve for that, we want to take this 1 and set it equal to this n over 4 to the k. So we get 1 equals n over 4 to the k. 4 to the k equals n. And so log base 2 of 4 to the k equals log base 2 of n. And so you get k equals 1/2 log base 2 of n. So that's the depth of the recursion at which things reach the base case. So finally, the last step is at this very last level, let's substitute that in for our general form that we've derived here. And so we get 3 to the power of 1/2 log base 2 of n. T to the n over 4k is just t to the 1, which, as you've assumed, is just 1, plus the sum from I equals 1 to 1/2 log base 2 of n of n over 4 to the I log n over 4 to the I. Okay, so now we have an expression for t of n that's expressed without any recursive calls and purely in terms of a function of n. So all we have to do now is find a theta bound on this. So let's first consider the first term. So recalling the property that c times log a is equal to log a to the c, we can note that 3 to the power of 1/2 log base 2 of n is equal to 3 to the log base 2 of n to the power of 1/2 equals 3 to the log base 2 of square root of n. Okay, and finally, in reasoning about this term, we're going to use the property that c to the power of log b is equal to b to the power of log c, which allows us to say this expression above is the same as square root of n to the power of log base 2 of 3. And so yeah, we now have an expression for our first term. Expressing this in even simpler terms gives us n to the power of log base 2 of 3 over 2. Okay, so as you'll observe, the exponent here is less than 1. And so now let's move on to bounding the second half. So a couple corrections from the previous part. So in this summation here, the bound should actually start at I equals 0, not I equals 1. And we forgot to include the 3 to the power of I term. Okay, so we looked at this summation that represents our recurrence t of n. And looking at this first term, we also showed that it can be re-expressed as 3 to the power, or n to the power of log base 2 of 3 over 2. And this exponent, if we evaluate it, we'll see that it's less than 1. Now moving back to the summation, the terms kind of look like they're in the form theta and log n with a bunch of other numbers appended. So let's see if we can formally prove that this is the case. So if we expand the terms, we'll notice that the first term is n log n. The second is 3n over 4 log n over 4, and so on. So if we consider just the first term and ignore the rest, we can see that this will be a lower bound, just because we're getting rid of other terms in order to recover just this first term here. Okay, so now that we've shown this lower bound, let's see if we can also show an upper bound of n log n. And a good way to do that is just to note that log is a strictly increasing function, which means that if whatever you put into the log function is larger, whatever the log function evaluates to will correspondingly be larger. And so what that tells us is that log of n over 4 to the power of I is going to be less than or equal to log of n. So now we have our summation. Let's simplify a little bit. And let's now use this thing that we just have shown to substitute. So we now know that this summation of terms is going to be less than n log n. All we've done is replace each of the log base log of n over 4 to the I terms with log n. And correspondingly, this term is also going to be less than the infinite sum, 3/4 to the I n log n. And so since the summation is over I, and n log n has no dependence on I, we can simply factor it out, giving us n log n, I equals 0 to infinity of 3/4 to the I. And so since this is an infinite geometric sum, we can use the formula for solving infinite geometric sums, which gives us n log n times 1 over 1 minus 3/4, which gives us our final result of 4n log n. And very clearly we can see that this is an upper bound for our original function, and so our original function is O of n log n. And so yeah, so we're basically done. We've now shown that the function is both omega of n log n and O of n log n, and so it must be the case that it's theta of n log n as we desired. And again, going back to the fact that the exponent on n over here is less than 1, theta of n log n is going to dominate that term. And so this is our final runtime, theta of n log n.
All right, so let's move on to problem 2. It says, given a sorted array A of n possibly negative distinct integers, we want to find out whether there's an index I for which A of I is equal to I. So to give you an example, let's say that we have an array that looks like negative 32, negative 16, negative 12. So this is index 1, 2, 3, 4, which is 4, 5, which is 6, which is 8. Let's say we have an array like this. So in this array, is there an index where a of I is I? Indeed, right? We have this one. So that's what the question is asking, and it's asking us to provide a divide and conquer algorithm that runs in O of log n. So in these kind of questions, actually, the runtime is a pretty good hint. So let's think about why that might be. Remember, this is a divide and conquer algorithm. Divide and conquer algorithms can be expressed with recurrence relations. So something t of something over something plus O of something. Now let's think about this. If we need O of log n as our final answer, that means that we cannot actually have something that is O of n here. Why not? Because remember, we compare d versus log base ba. If d is 1, we already have a runtime that's at least n. So it's not going to work. That means we can't do O of n work here. We could do maybe O of log n or something smaller, but this is a pretty good indicator that you cannot do a linear amount of time, a linear work in these kind of questions when you have O of log n. And moreover, let's also think about the similar ones that we've seen before. We've seen something that looks like this, right? 2t n over 2. What happens in this case? Well, whenever you have something that's like a and b are the same, log base a of a is always 1, right? So if a and b are the same, then you're going to get a 1 here. And remember, master theorem says that the answer is this, which gives n to the power 1. So we also cannot have something where these two are the same. So as in, we can't break into two problems that are each of size n over 2. So we need to really think about what our recurrence relation needs to look like. And I think that really helps. So one more thing to remember is binary search is O of log n. And what does the recurrence relation for binary search look like? In binary search, we just split the problem in half every time. We don't actually solve two separate problems. We just solve one. At each step, we split it by half. And how much work do we do? Well, we just do constant amount of work because we just check whether the middle index is what we're looking for, right? So this is what the recurrence relation looks like for binary search. Okay, going back. So we have Tn is equal to Tn over 2 plus O of 1 for binary search. What does this sort of look like? This is hard to tell that this would result in log n, so let's take a look. D is going to be 1, B is 2, and A is 1, right? So let's take a look at what log base 2 of 1 is. It's actually 0 because 1 is 2 to the power 0. And D is 1. D is 0, my bad. Because this is also n to the power 0. So we have 0 and we have 0. This is the equal case. And in the equal case, master theorem says n to the power d log n. But d for us is 0. So this is just log n. This is how we get the sort of log n runtime. Typically, this is generally how you would get a log n runtime. Just have like O of 1 and t of n over something. So, if it was t of n over 3, then the log base would be 3. But this is typically what recurrence relations look like for log n problems. Okay, so let's think of a log n algorithm for something like this. It would sort of make sense to be able to divide this problem into 2 and see what we can do from there. So one more point to note is the integers are distinct. Why is this important? It'll be clear in a second, but the integers need to be distinct and they can be negative. Okay, so let me erase this and keep our example so we can work from there. But at this point, I'm going to encourage you to pause and think about it. We know what the recurrence relation needs to look like. So try to reason about what kind of an algorithm this would be and what we would need to do at each step. Okay, so let me draw some more here and start with this example. Let's make one last one. Okay, so we'll start by looking at the middle element. Let's look at this. And we say, well, index 5 element 6. So now here's the question. Can anything in, let me erase this, can anything in this half of the array satisfy the property that we need, which is a of I is equal to I? Anything on this side? Well, this is where the distinct part becomes important. No, right? Because if this is 6 and this array is sorted and the integers are distinct, then this number cannot be 6 because this was already 6. So this number has to be at least 7. This number has to be at least 8, at least 9, at least 10. And so none of them can actually obey this property. Great. This is the crucial realization that you can just throw out this entire array. And now that you can do that, well, you have 4 elements left. This is the remaining part. Recurse. Just check the middle element. When in doubt, pick any one. We can pick this one. Now for this one, we have index 2 and element -16. We have to make the same reasoning, but on the other side, right? Can anything on this side of the array satisfy our property? Well, no, because this is -16. So this has to be at most -15. Sorry, it goes smaller. So this has to be -17, -18, and so on. So this can never be 1, right? And so we can just throw this out and then recurse here. And finally, we will hit this case where we say, all right, we found our answer. So this is pretty similar to binary search. This is exactly how you would describe the algorithm. The main idea, the way to write it is, well, we look at the middle element. So let's try to write the main idea. Look at mid element if index of if index is greater than the value. What does this mean? Well, this was the case where the index was less than the value. This is the case where the index is greater than the value. If index is greater than value, throw left. So as in we can throw out left half the array. Similarly, if index is less than the value, so if less than value, throw right. And finally, if they are, so let's scroll, let's see. Okay, if equal to value, we have our answer. Of course, you have to write these in coherent English sentences, but you get the idea. And how do you justify the runtime analysis for divide and conquer problems? This basically entails writing out the recurrence relation, explaining the recurrence relation. So in the sense, reading this off, there's a problem of size n. At each step, we can split it into a single problem of size n over 2, because this is because we just throw out half of the problem and we do constant amount of work. All we do is we check what is the index and value. We just compare them. That's it. That's constant. So this is how you would do a sorted array sort of problem, and O log n is a pretty good hint towards some recurrence relation that looks like this. Not always, but it's a pretty good hint. Okay, cool. Let's move on to counting inversions. First of all, let me just define what an inversion is by drawing out an example. Let's say we have something that looks like this. How many inversions does this array have? Here's how I like to count it. Well, this element is fine. It's sort of in place. So far, we've seen no problem. So no inversions here. This element is fine with respect to everything before it. So no inversions here. This element similarly is fine. This element is fine. This 2 is not fine. This 2 should actually be 1, 2, 3 places away. That's what. So this 4, well, is this fine with respect to this? Yes, these two are relatively sorted, so that doesn't count. But 4 and 7 is a problem. 4 and 5 is a problem, and the other two are okay. So we have 2 inversions. Again, 4 and 2 is not a problem. 4 and 7 is a problem. 4 and 5 is a problem. 4 and 3 is not a problem. 4 and 1 is not a problem. What about 1.5? 1.5 and 4 is a problem, so that's 1, 2, 3, 4, 5. And 3 we have, well, it's a problem. Sorry, this is not a problem. So 1 is fine. 2, 3. Okay, So in this case, we had a total of 3 plus 3, 6 plus 5, 11, 13 inversions. At this step, we need to sit back and think about how many inversions are possible in the worst case. Well, consider something like 6, 5, 4, 3, 2, 1. This one has no inversions. This one has 1 inversion. This one has 2 inversions. This one has 3 inversions, 4 inversions, and 5 inversions. So we have something like 1 plus 2 plus 3 plus 4 plus 5, which is whatever it is, it's going to be of the order of n squared, where n is the length of the array, and this is problematic. So the naive algorithm for counting inversions runs in, sorry, not theta, but O, right? Because in the worst case, it runs in O of n squared if the array is completely, let's say, unsorted. What we can do is develop something that works in n log n, and we need to think cleverly how to do that. So let's think. What if, and I'm going to follow the hint here, the hint says, modify merge sort to count during merging. Okay, so let's think about how we can do that. Let's say that I was able to split this array up into half, and I sorted this part and I sorted this part. Okay, so sorting this part gives me 1, 3, 5, 7. Sorting this part gives me 1.5, 2, 3, 4. Let's say I could do this. This is the merge sort algorithm, right? And the next thing we do in merge sort, as a reminder, is we maintain 2 pointers here, and then we walk through the array. So we say, okay, well, which of these 2 pointers is smaller? 1. So we move this pointer forward. Which of these 2 is smaller? 1.5. Which of these 2? 1.5 moves forward. Which of these 2 is smaller? 2 moves forward. Which of these 2 is smaller? Well, they're the same, so it's fine. We can just move 1. Which of these 2 is smaller? This one. Move 1. Which of these 2 is smaller? And then there's nothing here, so we just copy the remaining from here. 5 and then 7. This is the merge sort algorithm. And this final step is what is called the merge step of merge sort algorithm. So let's see how we can modify this merging step to also count the inversions. Let's think about this. Okay, so I'm going to copy over my 1, right? That's the first thing we did. Do I have any inversions so far in this list? Well, not exactly, right? Because it's just 1, so it's fine. What about this 3? Do I have any inversions? What about 3 versus 1.5? Well, now when I copy 1.5 over, what's going on? This had an inversion with this, and this, right? Because the position for this is actually supposed to be all the way here, is what this says. Aha. So then this counts as 3 inversions. So let's make a note of that. 3 inversions. And another thing to note is this number 3 actually is the size. So let's call these subarrays A and B is the size of remaining elements in A, in the sense that 1 has already been used up here. So the size of remaining elements in A. Cool. So 1.5 gave us 3 inversions. And now we're going to move this pointer forward. So let me erase this and move this pointer forward. This element has now been eaten up. Now we have a 2. Well, 2 is also giving me 1, 2, 3 inversions. Okay, so 3 and then plus 3. Okay. Move this forward. Now we have 2 3s. Let's take this one. We take this one, no inversions. Move forward. Now we have 5 and 3. Let's take this 3, we have to. How many inversions? Well, 1, 2, right? Because this should have been all the way here. Cool, so 3. So yeah, we copy over the 3 and we have 2 more inversions, and so on. So as you can see, this sort of an algorithm, it counts the number of inversions right at the end. Let's keep going. So this is 3, and we have this. Do we have inversions? Well, yes, we have 2 more inversions, so plus 2. We copy over the 4. Move this forward. Now we have no more inversions. Plus 5, plus, sorry, not plus, 5 and then 7. Right? And now, this was the inversions at the top level, but we also need to count the inversions in the intermediate levels, remember, because when we sorted this subarray, so when we sorted 2, 4, 1.5, and 3, internally there are inversions too, right? There are inversions between these two. For instance, 2 is fine, 2 and 4 is fine, 1.5 actually, this one has 2 inversions, and this 3 has, let's see, 1 inversion, right? So we also need to do this same inversion counting step in the intermediate recursive calls also. And then when we sum up all the inversion sums from all of our steps, we're going to get the final total number of inversions. And this, if we write out the recurrence relation, we have a problem of size n. We split it into 2 problems of size n over 2 each, and we do O of n work in the end to count the number of inversions. And just to recap, our final algorithm has been if taking element from A, this means that there were no inversions. If taking elements from B, then add plus equals length of remaining list A. This is the number of inversions we've added, because when we, for instance, when we consider this 4, well, the length of the remaining A is 2, and so that means we had 2 inversions. So this is our final algorithm, and you can justify this. All right, again, if you have any questions, feel free to follow up. And with this, I'm going to give it back to Nikhil to do the last problem.
So just as a general review for complex numbers, complex numbers are numbers of the form, complex numbers are numbers z that can be written in the form x plus iy. And x is referred to as the real portion of the number, and iy is referred to as the imaginary portion of the number. So one thing to note is that's very useful for thinking about these complex numbers is that there's kind of like a one-to-one relationship between these complex numbers and coordinates that are of the form xy. And these coordinates are actually used for plotting complex numbers in something called the complex plane. And this looks exactly like the xy plane. The only difference is instead of on the y-axis, instead of having 1, 2, 3, you'll have I, 2i, 3i, and so on. All right. So yeah, so then the x-axis is referred to as the real axis, and the y-axis is referred to as the imaginary axis. Okay, so now going back to the problem, number 4, we're asked to write numbers in the form r times cosine of theta plus I sine of theta. So this is actually a very useful form for complex numbers called polar form. And the easiest way to think about how to do this is to plot the complex number in the complex plane. So looking at the very first part, part I, our complex number is going to be negative square root of 3 plus I. So remembering our one-to-one xy mapping, this is going to give us the coordinate negative square root of 3, 1. So now we go about drawing the complex plane, and we plot the point at negative square root of 3 and 1. Yeah, so what we mean by polar form, so r times cosine of theta plus I sine of theta, that just means that we're changing from an xy coordinate to a coordinate of the form r comma theta. So this is what we want our new coordinate to look like. And just to give a couple additional definitions for what these two numbers are, r is going to be the distance of our complex number from 0, 0, or the origin, and theta is going to be the angle that is made with the real axis, or x-axis. All right, so how do we figure this out for this point that we have? So we want to figure out how far this point is from 0, 0. And so we can do that by computing, just using standard distance formula. And so we get that r is equal to the square root of negative square root of 3 squared plus 1 squared. And so this gives us r equals 2. So to find the angle that this makes with the x-axis, an important thing to notice is if we make a triangle with this point, we're going to have this angle be 30 degrees, this angle be 60 degrees, if we make a right triangle. And that just stems from the fact that this is a special right triangle, a 30, 60, 90 triangle. And so yeah, this is also another good way to see that r is 2, since if this side length is square root of 3, that means this side length is 1, which means the hypotenuse of this triangle is 2, just by properties of 30, 60, 90 triangles. Okay, and through that, we've also seen that this angle is 30 degrees, and we want the angle that's made with the x-axis, so with respect to this section here, so we want this angle. And so we can just see that that angle is going to be 150 degrees by computing theta equals 180 degrees minus the 30 degrees we have here. All right, so the common way of expressing angles in polar form is in radians. And so converting from degrees to radians, 150 degrees is equal to 5 pi over 6 radians. Yeah, so our final answer is going to be, the number is 2 times cosine of 5 pi over 6 plus I sine 5 pi over 6. Okay. Okay, so moving on to part 2, we're asked to find the 3/3 roots of unity. And it's good to recall that the roots of unity for degree n, where n in this case is 3, are numbers of the form where z to the n is equal to 1. Yeah, so as a general rule, the 3/3 roots of unity are going to be, so as we covered in the previous part, complex numbers are of the form rho times cosine of theta plus I sine of theta. So this rho is going to equal 1 for roots of unity, and the theta is going to vary. It's going to start at 0 and go up to 2 pi. And the multiples, it's going to go up by multiples of 2 pi over k, where, and it's going to go up by multiples of 2 pi over n, where again, n is our degree, in this case, 3. So what that tells us is that the values of theta for the third roots of unity are theta equals 0, 2 pi over 3, and 4 pi over 3. All right, so plugging these values into this formula, we get that the three roots of unity are going to be cosine of 0 plus I sine of 0, cosine of 2 pi over 3 plus I sine 2 pi over 3, and finally cosine of 4 pi over 3 plus I sine of 2 pi over 3. Yeah, so it's kind of interesting to note that this first one, since sine of 0 is 0 and cosine of 0 is 1, this is just 1, and this is just going to generally be the case. You're always going to have a root of unity that's 1, and that very obviously satisfies this equation. Just a cool thing to notice. Okay, so now going back to what we discussed in the previous part about graphing complex numbers in the complex plane. Roots of unity tend to have a very interesting property. So if we draw a circle of radius 1, this is going to be I, negative I, 1, and negative 1. The roots of unity are going to be evenly spaced on this unit circle in the complex plane. So the very first root of unity is going to be at 0. The second is going to make an angle of 2 pi over 3, which is equivalently 120 degrees. And the third one is going to make an angle of 4 pi over 3, or equivalently 240 degrees. So it's kind of cool to notice that, like, these two roots of unity, the 120 degree angle and the 240 degree angle one, they kind of form a pair, in the sense that their x coordinates are, or their y imaginary coordinates are equivalent but opposite. And another thing to note is that their x coordinates are each half of 1. They're each equal to 1/2. So this length here is going to be 1/2. And so that segues into part 3, where you're going to have the case where, because of this like symmetry that you can see in the roots of unity, their x coordinates are going to sum to 0, since you have 1 here and you have 2 negative 1/2s here. And their y coordinates are also going to sum to 0, since this one has no y coordinate, and the y coordinates for these two angles are exactly opposite. So the answer to part 3 is that the roots of unity simply sum to 0. So continuing off of this property that we noticed, it's actually a general trend that if you plot the roots of unity on the complex plane, they're going to be kind of symmetrical. So they all are equidistant from each other on this unit circle. And this is especially useful when we have nth roots of unity where n is a power of 2. Okay, so for the purpose of this problem is mainly to get you guys geared up for learning about the fast Fourier transform.